Okay, so we're going to go over the homework for Module 6. A lot of this will be returns of portfolios and do descriptive statistics of those. So this is our first one. This is looking at uh, calculating the total return. So we have an initial price of the stock, and unfortunately, the price did decline to 79.50 from 100. But we did also get a dividend. And so they ask us, what is the total return? What is the dividend yield? And what's the capital gains yield? You see the equation for total return is the difference in the share price, the new share price of 79.50 minus the old price of 100, plus any dividends that you receive divided by the total, the initial price, the old price. And that gives us our total return. You can break that into two pieces. So if you just say the dividend piece divided by the old price, that's your dividend yield. If you just take the change in price divided by the old price, that's the capital gains yield. So the total yield is always going to be equal to the dividend yield plus capital gains yield. But hopefully you see mathematically why that's the case. Okay, we also have a question about nominal and real returns. So remember, nominal returns do not, that's what we would say, right? Nominal means named, right? So it doesn't account for inflation. So what we're going to do is use the Fisher equation. Irv Fisher came up with this over 100 years ago. But we'll just plug that in to calculate what our real return would be. So they told us what the nominal return, that arithmetic mean, right? They gave us that to begin with. But you notice you can't just say 14.3 minus 4.2, right? Instead, it's 1 plus each percentage, and then you have to divide it and subtract 1 from that quotient. And that will give you what the real return is. So in this case, it's a little over 9.5%. Okay, here's another one using that same Fisher equation. They give us long-term government and long-term corporate bonds, and then we have inflation. And they just want us to pick apart what it would be in real terms, not the nominal terms. So we were given nominal returns, and then we do that same calculation that we would have done before in the last problem to calculate what is the real for government and the real for corporate. Okay. Again, just notice you can't just subtract inflation from that, right? It's a little more complex than that. Okay. Now this is something that you may not have done since Stats 260 or a similar course. But just to go over mean, variance, and standard deviation, we get a set of returns for two stocks, X and Y, over 5 different years. They say calculate the average return. You've calculated averages before, so in this case, for this arithmetic return, right, we're going to add those returns up. Some are positive, some are negative, right? But we add them together and then we divide by the number of observations that we had, right? So it's just like if you had a bunch of different friends with different heights, you could add the heights up, divide by the number of friends, and that would tell you the average height. Do the same thing to get our average return. Okay. So for variance, it's a little more complex because what we're going to do is look at the average returns, the 7.9 for X and the 13.88 for Y. And then we look at each year's returns and see how different from that average it is. And that's why you see on the right hand side, 0.219, right? Because that's that first year, 21.9%, minus 0.0792, that's the 7.92%. So you subtract the average from the return and pay attention. Some of these are going to be negative returns. And you could even have a negative average. We do not, right? But you just want to make sure we get our signs correct. And if you notice for variance, all of those differences, right, between our return and the average return are squared. So once you square all of those terms, you add them together. And instead of dividing by the number of observations, it's n minus 1. The reason we use n minus 1 has to do with degrees of freedom. I don't want to get too into the math. but just think, okay, as a sample, average will be divided by n, standard or variance will be divided by n minus one. I started to say standard deviation. Standard deviation is the square root of variance. So once you calculate the variance for each, you just take the square root, right? And once you take the square root, you can then convert that back into a percentage, just like you have for your average return. The reason we'll normally talk about average return and standard deviation is because with a large enough sample, it looks to be normally distributed, right? It's a central limit theorem. And that gives us a lot of ability to think of things in the same terms, right? So right now we were talking about percentages, but if our average was in feet, then our standard deviation would be in feet and our variance would be in square feet, right? Because we got that squared term. So it's a little more thought, that you have to go into this. But if you take the square root, we can say, this average, and then we have a standard deviation. So if we want to talk about confidence intervals, we say plus or minus some multiple of the standard deviation. So that's why we're going through this again. Okay. Here's a couple looking at risk premium. This question's pretty long, so I broke it up over a couple of different slides. So the first one, they just give us 6 years of returns for large company stocks and for U.S. Treasuries, right? T-bills are short term. We'll talk about Treasuries a bit more in the future too, but a T-bill, a T-note, and a T-bond are just different time periods. So T-bills are the short term, T-notes are the medium term, and then the bonds are long term. So this is a short term rate, and this is our stock returns. And then if you notice stock returns, some are positive, some are negative, because some years they go up, some they go down. Treasuries tend to hold a lot more stability, right? And so you see those returns. They want us to calculate the arithmetic mean for these over this time period, calculate the standard deviation, and then looking at the difference in those two, we're going to come up with what the risk premium, because the large company stocks are risky, U.S. Treasuries are not risky. And so we're going to calculate what is that risk premium, and then how much standard deviation is there around that risk premium. So next slide. Right. So for that first part, how do we calculate, these averages? Well, just like we did before, we're going to add them up and divide by the number of observations, right? And so our observations are 6, right? 6 years total. So you just add them up, divide by 6. When we calculate variance, that's like the last problem. So we look at each return and then we subtract off that average that we calculated, square that difference, add those up, and then instead of divide by 6, we'll divide by 5. Again, we are always going to divide by what they call n minus 1, right? So you take the number of observations and subtract 1 from it. So you do that for both the corporate and our T-bills, right? And so you'll end up with both the standard deviation for each, right, by taking the square root of those variances. So that'll answer the part A of the question. For part B, the difference is we're looking at that observed risk premium, and we're saying how different our risk premium is year by year over that observed average. And then by squaring those differences, and then again dividing by 5, because you have 6 observations, so n minus 1. That gives us a variance, and then we calculate the standard deviation by taking the square root of that. I know that one was a little long, but it was really just because we have to sort of show this math. And I don't know the tricks really to remember some of these, but I always just know variance is standard deviation squared. In fact, when we write it for average, we put a lowercase mu, which actually looks like a U. And then for standard deviation, we use a lowercase sigma, which is sort of like a circle with like a little bit of a flap on the top. And then variance, we write sigma squared, lowercase sigma squared. So this is how I always remember variance is the squared, sigma squared. And so we're always going to square what we're using to calculate those terms. Okay, here's one where we're calculating what our expected return is going to be, but this is with that confidence interval, right? So we were told that we have an average return of 6.9, our standard deviation's 9.9, and they're saying, okay, what would we expect to see 95% of the time? And 95% of the time is really close to 2 standard deviations. So that's what we're going to do. You just say 6.9% plus or minus 2 times the 9.9%. And that gives you anything from negative 12.9 to 26.7. So 95% of the time on a given year, I would expect it to be somewhere between those two numbers. And if we wanted to go to 99% of the time, instead of 2 standard deviations, we'll just use 3, right? And if you notice, those bands are a lot wider, right? Because we're adding in that extra standard deviation. But then only 1% of the time would I be incorrect, where before with those tighter bands, it's 5% of the time. Okay, and here's looking at arithmetic and geometric average. So the averages that we've been calculating have been arithmetic. That's where you add them up and divide by the number of observations that you have. For geometric returns, what you do is you would say 1 plus the return for each time period. Once you have those, you multiply them together, get the product of all of that. And then instead of saying divide by the number of observations, you would take the nth root. So if you have 6 observations, you take the 6th root of it. Once you do that, you subtract 1. We normally use geometric returns if you have year-on-year returns. So year 1, year 2, year 3, year 4, we almost always will use geometric return. If it is, well, there's some probability we're in a booming economy, some probability we're in a flat economy, some probability we're in a recession, some probability we're in a depression, whatever it may be. If they're distinct probabilities and you'll be in one state or the other, we normally use arithmetic return. Okay, but geometric is really important if what happens in one year impacts the results the next year. And so that's why we use that on year after year returns, because my return one year will impact my return the next year, right? If I doubled this year and I double again the next year, that's 4 times total, right? But yeah. Okay, here's some more about calculating the average. And again, this one's a little long, but there's a lot of parts to it. That's why it's over multiple slides. But they give us T-bill returns for 8 years, and then they tell us what inflation is over those years. So they ask us to calculate the average return and the average inflation, which we've done that calculation several times already. We're going to do that one more. And then what's the standard deviation, right, from that? And then what is the real return for those 8 years, right? So those years 1 through 8. What is our real return? And then what's the average real return of T-bills over that time? Okay, so the way we'll calculate that, we have to go to real returns. So we have our return, we have what the inflation is, right? So that we can calculate what the real return for each of those, right, to account for that inflation piece, right? And then once we have that, we can also sum the returns and inflation and divide by our observations and get what those average numbers are, right? And then we have what our average is going to be, so we can calculate what the variance is, because we have the difference in our return and what the average return was. Based on that, we get variance. And then we can calculate what the standard deviation is because it's the square root of that. And then for variance of inflation, we get what the actual inflation was. We calculated what our average inflation was, right? And so we would again divide that. We're going to divide by 7, not 8, again, because it's n minus 1. And then the standard deviation is going to be the square root of that variance, right? So we have observed real returns that we're able to calculate. What would that be over that time period? So we calculated that for each of the years, and then we were able to divide by the number of observations and get what our observed return was. So if our real return is minus 6.5%, what that means is while we're getting money from the T-bills, the money we're receiving doesn't keep up with the increases due to inflation. So we can be going up, but from a real standpoint, we're actually losing money because of that loss of purchasing power. Okay. In this problem, this is exactly how it was stated. They tell you to use the norm dis function in Excel. You actually don't have to in this one, the way it's laid out. I think all their probability, they just tell you to use that. If you do play around with that norm dist, you just type that as equals norm dist, and then you open parentheses. They're going to ask you, okay, what's your mu? And that's that little u that you see near the bottom. Kind of looks like a U with a stick in the front. That's a lowercase mu. That's your average. You see the little circle with a, I don't know, like bangs coming off of it. That's a lowercase sigma. That's your standard deviation. And then the X value that we would look at is what is the number we're concerned with. Now we're saying what's the probability that you lose money? And so that's the probability that you have less than 0 return, right? If you have a 0% return, you neither gain nor lose money. So if it's that we will lose money, then it's everything less than 0. So we look at how far 0 is from our average return, right? And then we divide that by what is the standard deviation, and we find out that that is a little less than half a standard deviation below. It's minus 0.4197. And so if you look at the probability of the Z of minus 0.4197, that's about a 33% probability. So about a 1 in 3 chance that you lose money given this average return and this much noise around that. Okay, here, this one, again, there's just more parts to it, but we're still just going to be calculating probability. I just, again, had to split this up over a couple of slides. So they're telling us that we have long-term corporate bonds. We got T-bills. They tell us the average return and the standard deviation for those. And then what's the probability that it's greater than 10% or less than 0%? Now we did 0 already, so we can see that. But we're also going to do 10%, and it would be the same thing, only we're using X as 10 instead of X as 0. And so let's see, we do that for both the corporate and the T-bills. And then at the end of 1 year, the return of long-term was minus 4.8. How likely is it that it would recur in the future? T-bills had a return of 11.2%, 11.02% in the same year. How likely is such a high return, probable? So what we're looking at is we also got this one really unusual return, and we want to see how unusual that is. That's what C is. So we'll start with A. Again, if you notice the X minus mu divided by sigma, right? How far is that from the average? And we divide that by the standard deviation. So the first Z-score we get for 10% is 0.4457. That works out to about 32%. And for less than 0, it's about 26%. When we're looking at the T-bills, we calculate the exact same way with 10 and 0, but our mean and standard deviations are different, so we have to put those in. And this one, you notice that Z3 is 1.64, so it's, over 1.5 standard deviations, and then minus 1.29, so almost minus 1 1/3 standard deviation. So The T-bills, as you see, because that standard deviation is so much smaller, um, to get those same numbers of 10 and 0%, it requires more of those, right? So it's less likely to occur. And then if we're going to calculate what the long or the return to be that unusual, then we calculate, 12%, and then 2.58% because those were rather unusual, but not impossible, right? In fact, when we build those confidence bands at 95% interval, that means 5% of the chance, 5% of the time, 1 in 20 chance that any observation would be outside of that. So as much as we're like 95% confidence, we do know that we will have things that fall outside of that. In this one, we're going to look at portfolio weights. So we have two different stocks, 150 shares of A and 125 shares of B, and they each have their own price. And so they're just asking us to calculate what those weights will be. We're going to come back to this weighted portfolio, but this is just to sort of get us started. So the total value of the portfolio is just the number of shares times the share price. And we sum those up across all of our various stocks. In this case, we only have two, right? And so for the weight of each, you would just say, okay, proportionately, how much is in A and how much is in B? And that's really all the calculation is. We'll do some descriptive statistics and work, and we also use those percentages later. Okay, and here's one looking at like states of the economy. So I think I used this as an example earlier when I said sometimes you'll look at these different states and it's like either things are going well, things are going poorly. This one we have two states of the economy. A lot of times I'll say these problems written with 5 states of the economy, sort of a really good, pretty good, kind of flat, kind of bad, really bad, But whatever it is, you come up with some probability. Those have to equal 1 when you add the probabilities up. And then you see what the returns would be in those. And all we do is take the probability that we're in that state times the return we get for each of the states. Now you might say, well, that's weird. Shouldn't we add them all up and then divide by the number of states? Well, the states are already weighted by the probability. So since those probabilities, I already said they have to equal 1, right? That means at the end, what we do is divide by 1. So we're perfectly fine. But this allows for us to not give equal weight to everything and instead give more weight to the things we consider to be more likely. All right, and that's what we're doing here. So even though we're going to get negative 11% or plus 23%, we would say on average we expect to get 10.42%, even though we know we're going to either lose or gain, much more. Excuse me. Okay, so this is one, like I said, it's going to be a little more complex. So we have two different states of the economies with their own probabilities of occurring. And then we have 3 different stocks that make that up, A, B, and C. And then we are told that in A, what's the expected return on an equally weighted portfolio? So we're going to have 1/3 of our investment in each of those. And then the part B is, more complicated in a bit because it says, well, what if it was 22% in A and 22% in B and then 56% in C? And then we're going to calculate what that variance would be. So expected return, we just have to look at each state of the world. So in a booming economy, we would expect 10% on our A, 4% on our B, and 35% on C. You add them up, divide by 3. Same thing for the bust economy, add them up, divide by 3. You'll get each of those. And then you could take those same calculations, that 16.33% and the 13%, and you just multiply them by the probability of that state. So I got a 67% chance of 16.33%, and I got a 33% chance of 13%. And what I end up getting is 15.23. It's going to obviously be between 13 and 16.33, but how far between the two, it's based on that percentage weight. Okay, and so calculating variance, like we've calculated our average, so what we're going to have to do, we've calculate the return of the portfolio in each of those three, or each of those two states, the boom and the bust economy. But remember, it's 22% A, 22% B, and 56% C. So we're going to weight them that way instead of 1/3 each. And so our returns would be 22.68% in the good time, 3.48% in the bad time. We just multiply each of those returns times the probability, and that gives us what the expected return is. So this is like the average return, but we will talk about expected return because, we know there's no guarantees, right? But just given what we know, this is what we expect to get, at the end of the year. So we have our expected return, and we also know that what the real returns would have been, 22% or 3%. So to calculate variance, again, you just say, what's my actual minus my expected, the average value, right? And then you square those differences, right? Now, once you do that, before when we calculated variance, we would just add them up divided by n-1. It's a little different this time because it's not equal weights. So before with variance, we were calculating it with everything being equal. Now we're saying there's different probabilities in different states. And so we actually are going to weight that by those probabilities, right? And that is going to give us what the variance of that portfolio will be. And I know you're saying, hey, can I do some more of these? But don't worry, we do have one more, right? Here's one with 4 different economic states. And if you notice, those probabilities are different for each of them, right? And we're looking at 3 different stocks, and they all have their own returns in each of those states. Then they tell us that we're going to have a portfolio that's 29% in A and C, and then 42% in B. And then they want us to calculate the expected return, the variance, and then standard deviation. Again, standard deviation is just going to be the square root of the variance. We know that. So once we calculate B, we'll take the square root of that for C. And then the expected return, we know that the first thing we have to do is calculate what we're looking at for each state of the economy, the boom, good, poor, and bust, based on the weights for A, B, and C to calculate what we would expect to have as a return in each of those. We then multiplied those returns times the probabilities that were in those states. That gives us our expected return of the portfolio. And then what we have to do is say, okay, I know what the expected return of the portfolio is, but what was my actual return for each of those states? So we have the boom, and its expected return, goods return, poor's return, bust return, right? And we're going to compare each of those to that 11.24%. You square the difference in those two numbers, and then again, you're going to add them up, but it's going to be weighted, not equally, but instead weighted by the number or the probability that you're in that state. And again, those probabilities have to equal 100%. Or equal 1, right, when you add the probabilities together. So once you do that, you'll calculate variance. And again, the square root of the variance will give you the standard deviation. And again, we care about that. The expected return to standard deviation is how we calculate those other probabilities, like what's the percentage chance we lose money, that kind of thing. So that's why we always go back and calculate standard deviation and not just stop at variance. Okay, so beta is a measure of how risky a stock is relative to some standards, such as the market. This is, we have an expected return. We do have a risk-free rate. We do know that the market risk premium is 7.3%. So they're saying, what is the beta, right? So the expected return on a stock is going to be equal to the risk-free rate plus the market risk premium times beta. Right? They told us what the expected return was. They told us the risk-free. They told us what the market risk premium is. So we just solve for beta. And this same calculation that we do for stock, we can also do for portfolios, right? So they tell you, hey, I got this portfolio. I've got these various stocks that are in it. These stocks have their own betas, right? So what is the portfolio beta? So what we're going to do is just weight it based on the ownership of stock. So if 34% is in stock Q, then 34% of our beta is Q's beta. And 18% is in R, so 18% of the portfolio's beta is equal to R's beta, right? Again, those percentages should add up to 100%, right? And you just multiply those weights times those betas, and that will give you the beta of the portfolio as a whole. In this case, you see it's 1.32. Okay, this one, I know there's a few different pieces there, but it's because there's a larger table, and we're just going to calculate the returns and betas based on how much of the portfolio is in our risky asset. So we only have two things we're buying, right? We're going to buy our risky asset W, which has an expected return of 13.3%, and the beta is 1.31. We do know we got a risk-free rate of 4.56%. And then we can weight ourselves between asset W and the risk-free rate. So if you see the table where it says percentage in asset W 0, that means you only own the risk-free rate, right? So your expected return is going to be the risk-free return, and there is no beta because there's no risky asset. It's just the risk-free rate, right? If you look at the 100%, that is only owning W and no risk-free. So the expected return is equal to asset W, and the portfolio beta is equal to the beta of W. So just so you understand, in the table, that's what those two particular numbers are looking at, okay? Anything that's between 0 and 100, you do not own some percentage of W, and instead you've invested that in the risk-free rate. Anything that's over 100%, what that means is we borrowed at the risk-free rate and put more money in. And when you see the answers already, so no secret, as you increase that, the expected return is much higher, right? You see it went up and up and up, but also your beta went up, right? So what you're doing is you're introducing more risk because you borrowed money, right? And this is where we get the term leverage, right? Because adding that ability to borrow at the risk-free rate allows you to get much higher rates of return, right? And this is why you'll see companies using borrowing for these types of investments, because you pay back exactly what you borrowed, but any profits you get to keep, and so your returns are higher. But you have introduced additional risk because now you can default. It's not a free lunch. It's not, free money or anything like that. But I just want you to understand what we're calculating with that. So that all that being said, what we're going to do to calculate the beta of the portfolio, right? What we're doing is we're just going to be weighting it between 1.31, which is W's beta, and 0, which is our risk-free beta, right? And so the beta of the portfolio is just going to be 1.31 times the percentage of W, right? And so all of those, you just put in between 0 and 1.5 for 150%, multiply that by 1.31, and that gives you the portfolio beta, okay? If you try to get the expected return, then all we have to do is use the CAPM, capital asset pricing model equation, right? The expected return on any portfolio is going to be equal to the risk-free rate plus the market risk premium times beta. So how can we get market risk premium? Well, we were given our beta, we were given our return, and we were given our risk-free rate. And so by using that, we're able to calculate what the market risk premium is. And then using that, we can calculate what the expected return is for any, value of the weights. All right, so we just have a few more problems to go here. This first one is looking at under and overvalued. There's a lot, to kind of explain that. I know it looks like the the selection is so easy, just over under. Um, anything that's overvalued means that it costs too much given its return. Anything's undervalued means it doesn't cost enough given its return. So that's what we're looking at. They give us a beta and the expected return. They tell us what the risk-free rate is and the market risk premium. So if you just use the risk-free rate and the market risk premium and you plug in those betas, it'll tell you what your return should be. So we expect Y to have a return of 15.33%, and it's only 15. So I'm going to pay too much because I should be getting 15 and a third, not 15. So that's overvalued. I want to sell. And for stock Z, I calculate that the expected return on Z is 11.06, and I'm getting 11.4. That means it's really cheap in the market, and I can go and buy it. So there's two different ways. The reason that answer is so long, there's two different ways to answer it. They're both shown there, but just keep in mind, all we're trying to say is this worth what I have to pay for it or not? Okay, so we're gonna jump back into portfolios here. So this one, we have a stock that has a beta and expected return. They tell us what the risk-free asset is, and then they say, let's build some different portfolios. So question A says, what if we equally invested in the risk-free and then our stock, what would our expected return be? If the portfolio we build has a beta of 9.2, what are the weights? And those two weights have to equal 1. And then if the expected return is 12.2%, what would be the beta of that portfolio? And we're going to calculate that. And then if a portfolio has two assets with this particular beta, what are the portfolio weights? So D looks a lot like C. But for the weights, they always have to equal 1. And if you notice on D, that's bigger than 1, but then the other weight is negative. Again, that just means that we're going to borrow money and invest it because that's what's going to allow us to drive that beta up even higher, right? That's how they got that beta of 2.52. So, we'll just look at A first, right? So they just have it's equally split between the two. I get 13% on one, I get 4.5 or 4.4% on the other, right? You add those up, divide by 2, and we expect to get a return of 8.7, right? So between those two numbers. For B, what we're going to do is say, okay, what would the beta need to be, right? We know it's 0.92, right? And so if I know that my stock has a beta of 1.32, and then obviously my risk-free asset has no beta, right? Beta of 0. Then all I'm going to do is take the 0.92 or the 2.52. We'll do that one in a minute, right? But you just take that number, divide by the 1.32, and that'll tell you what percentage of your portfolio would be invested in that. And then the risk-free asset is just 1 minus that weight. Because again, the weights have to equal 1, right? And so everything that's not invested in stock is in the risk-free asset. Okay, so I'm going to go ahead and skip on to the next one to show you the beta calculation, right? So while our risk-free has a beta of 0, that doesn't mean that our portfolio has a beta of 0, right? Because we do have that risky stock. So our expected return is 12.2%. We know the expected return is equal to the risk-free, that sort of thing. So by rearranging those terms, right, then we're able to calculate what would be in stocks. 0.907 is in stocks. The remaining, under 10% is in that risk-free bond. So you just take the percentage in stocks and multiply it by the beta, and that would give you the beta of that portfolio. So to get 12.2%, it would require the creation of this portfolio that's 90.7% stocks and 9.3% in the treasuries or the risk-free asset, and then the combined beta of that would be 1.2. And then D, we're also solving, for the beta of the portfolio. And if you notice again, this was one where it was like, wait, it's 2.52 divided by 1.32, I get 1.9091. So what I'm getting is I need to borrow a lot of money and then invest that in stocks. So it's almost twice my money investing in stocks, but that's how I can get my investment in something that's got the 1.32 beta and crank that up to 2.52 beta. All right, and the last problem we're going to go over is our portfolio building. Okay, so we have $100,000 to invest. We're going to buy DF or risk-free asset. We're going to have to invest it all. That's why I say you have to, the weights have to equal 1, right? Because we're going to invest all of our money. We're going to create a portfolio that has an expected return of 11.1%. That's our target. We're assuming that D's expected return, F's expected return, and the risk-free rate are given. And then if you invest 50,000 in D, how much do you now need to put in F? And then the remainder obviously would go in the risk-free asset. So we know that we're going to set this equal to 11.1% is equal to 50% of D plus some percentage of F. And then the remaining percentage of 1 minus what's in D minus what's in F is our risk-free. And then we would multiply that by the return of the risk-free. You just do all of that math, and then we get that the amount would be 0.1915. Excuse me. And then we know what the risk-free asset is, that the remainder 0.3085. But they're just asking us how much to buy. We had $100,000. 0.1915, that's where it rounds at least. But you know, if you do more digits, then you get that $19,148.94, which is, you know, again, like a little over 19% of the 100,000. So 50% is in D, about a little over 19% is in F, and then the remaining a little over 30%, almost 31% is in the risk-free asset. So I hope that answers any questions you have on this. If you do have anything, please do not hesitate to reach out to me, and we'll go from there. Thank you.